Arrival in the prehistoric era. In a desperate bid to solve the global food crisis, a team of scientists, engineers, and survival experts embarked on an unprecedented mission to travel back in time to the Mesozoic era and domesticate dinosaurs for sustainable food production. The team was equipped with state-of-the-art technology, including heavy weaponry, tranquilizers, strong chains, DNA modification labs, fencing materials, large vehicles, and heavy machinery. The goal was clear: domesticate dinosaurs to provide a sustainable source of meat and eggs, thereby alleviating the pressure on modern agricultural systems and ensuring food security for future generations. Upon arrival in the late Cretaceous period, the team immediately began constructing a massive army-style camp. The camp was designed to withstand the harsh conditions of the prehistoric environment, complete with towering walls and reinforced roofing to protect against aerial predators like Quetzalcoatlus. The landscape was teeming with prehistoric flora and an array of towering beasts, presenting both opportunities and significant threats. The team knew that their survival depended on their ability to adapt to this hostile environment and establish a foothold in this ancient world. Scouting the terrain with drones. The first task was reconnaissance. Aerial and land drones were deployed to survey the area, mapping out dinosaur hotspots and potential threats. The drones captured stunning footage of immense herds of herbivores like Brachiosaurus and Triceratops, as well as lurking predators such as Tyrannosaurus rex and Utahraptor. The data collected by the drones was analyzed to identify migration patterns, nesting sites, and regions rich in plant life suitable for potential domesticated species. The drones also provided valuable information about the terrain, including the location of water sources, natural barriers, and areas with dense vegetation that could be used for concealment. This information was crucial for planning the next phase of the mission: harvesting dinosaur eggs. Harvesting the largest dinosaur eggs. The priority was finding the largest eggs to determine their nutritional value. The biggest eggs belonged to the Hypsilosaurus, a titanosaur that laid eggs nearly the size of basketballs. The team carefully approached the nesting sites, using tranquilizers to subdue any protective parents. After securing a collection of these eggs, laboratory analysis confirmed their exceptional nutrient profile. Hypsilosaurus eggs contained an unprecedented balance of proteins, vitamins, and minerals, making them a superfood over 100 times more nutritious than modern chicken eggs. The discovery of these nutrient-rich eggs was a game changer. The team realized that if they could successfully farm these eggs on a large scale, they could provide a sustainable source of nutrition for millions of people. However, the challenge was to find a way to domesticate the Hypsilosaurus and other large herbivores to ensure a steady supply of eggs. Capturing and domesticating herbivores. With the initial food source secured, the focus shifted to capturing baby herbivores for domestication experiments. The team targeted young Maiasaura, known for their nurturing nature, as they were more likely to adapt to human interaction. The Maiasaura were successfully trapped and studied, and several species displayed varied reactions to captivity. Parasaurolophus, for example, adapted well to human interaction, quickly learning feeding schedules and showing signs of trust towards their human caretakers. However, others such as Stegosaurus proved difficult. Their defensive tail spikes and stubborn nature made them nearly impossible to tame. Despite extensive conditioning efforts, some species resisted all attempts at domestication. The team also experimented with different methods of domestication, including positive reinforcement, controlled feeding environments, and even genetic modification. Some species responded well to these methods, while others remained fiercely independent and resistant to human influence. The challenges of domestication. While some species adapted to captivity, others presented significant challenges. Stegosaurus, extremely territorial and resistant to confinement. Their defensive tail spikes made them dangerous to handle, and their stubborn nature made them difficult to train. Ankylosaurus, thick, armored skin made medical treatment difficult. Their slow-moving nature and tendency to curl up into a defensive ball when threatened made them challenging to manage. Triceratops, prone to aggressive behavior, often charging at fences and barriers. Their large size and powerful horns made them a formidable challenge for the team. Iguanodon, surprisingly cooperative and quickly adapted to feeding routines. Their relatively docile nature made them one of the easiest species to domesticate. Shantungosaurus, enormous size required extensive resources and containment strategies. Their sheer bulk made them difficult to transport and house, but their gentle nature made them a promising candidate for large-scale farming. Each species required different approaches in their domestication attempts. Some responded to controlled feeding environments, while others resisted all forms of human interaction. The team realized that a one-size-fits-all approach would not work and that they would need to tailor their methods to each species' unique characteristics. DNA modification for better domestication. For species too wild for direct domestication, genetic modification provided an alternative. The team's DNA modification labs were equipped with the latest technology, allowing them to selectively breed and alter the genetic makeup of certain species. The goal was to create more docile versions of these dinosaurs that could be farmed efficiently. Selective breeding and DNA alteration were applied to species like Edmontosaurus to create more docile versions capable of being farmed efficiently. The team identified specific genetic markers associated with aggression and territorial behavior and worked to suppress these traits in future generations. Meanwhile, the larger, more aggressive herbivores such as Shantungosaurus were kept in specialized enclosures for further observation. The potential to alter genetic markers for increased growth rates and docile temperaments became a critical aspect of the project. By selectively breeding dinosaurs with desirable traits, the team hoped to create a new generation of domesticated dinosaurs that could be farmed on a large scale. Slaughtering and processing for meat. Processing dinosaurs for meat posed significant challenges. Some species, such as Hadrosaurus, possessed tender, flavorful meat akin to modern beef, making them prime candidates for farming. Others, such as Therizinosaurus, had excessively tough and fibrous meat, rendering them difficult to process. The team quickly realized that not all dinosaurs were suitable for meat production and that they would need to focus on species with the most desirable meat quality. To slaughter large dinosaurs efficiently, AI-operated heavy artillery was developed. A specialized tank shell-sized bullet was engineered to bring down the larger species without damaging excessive portions of the meat. The team also developed specialized butchering tools and techniques to process the thick hides and tough muscles of certain species. Identifying the best dinosaur meat. The team conducted extensive research to identify the species with the most desirable meat quality. The following species were found to have ideal meat quality. Hadrosaurus, tender, flavorful meat comparable to modern beef. Hadrosaurus meat was rich in protein and had a mild, pleasant taste, making it a favorite among the team. Iguanodon, lean, high-protein meat with a mild taste. Iguanodon meat was easy to process and had a texture similar to modern poultry. Edmontosaurus, easily processed and nutritious, with soft-textured flesh. Edmontosaurus meat was versatile and could be used in a variety of dishes. However, not all species were suitable for meat production. The following species were found to have poor meat quality. Therizinosaurus, tough, fibrous meat, nearly inedible. The meat was difficult to process and had an unpleasant texture. Ankylosaurus, excessively chewy and difficult to prepare. The thick, armored hide made butchering a challenge, and the meat was tough and unappetizing. Stegosaurus, slightly edible but lacked desirable taste and texture. The meat was tough and had a strong, gamey flavor that was not appealing. The team also identified species that required special processing due to their thick hides and tough muscles. Ankylosaurus, armored hide necessitated specialized tools for butchering. The team developed new techniques to remove the thick skin and access the meat beneath. Triceratops, thick skin and bony frill made conventional processing ineffective. The team had to develop new tools and methods to process the meat without damaging it. Shantungosaurus, enormous size required extensive logistical planning for meat retrieval. The team had to develop new methods for transporting and processing the massive carcasses. On the other hand, some species were found to be easily processed. Iguanodon, soft skin allowed for quick butchering. The meat was easy to access and process, making it a prime candidate for large-scale farming. Edmontosaurus, suitable for large-scale farming due to manageable body size. The meat was easy to process and had a pleasant taste, making it a popular choice among the team. Utilizing byproducts for maximum efficiency. efficiency was paramount in utilizing every part of the harvested dinosaurs. The team recognized that byproducts could be just as valuable as the meat itself and worked to develop new uses for these materials. Thick hides from Ankylosaurus were repurposed for armor and protective gear, proving invaluable for personnel safety. The hides were treated and processed to create durable, lightweight armor that could withstand the harsh conditions of the prehistoric environment. Triceratops' horns and teeth became essential tools and weapons, ensuring sustainability within the prehistoric environment. The horns were sharpened and used as spears, while the teeth were fashioned into knives and other cutting tools. Even dinosaur waste contributed significantly. Herbivore dung provided an excellent natural fertilizer, boosting agricultural production in the experimental farming zones. The team collected and processed the dung to create a rich, nutrient-dense fertilizer that was used to grow crops and sustain the camp's food supply. Conclusion: the dawn of a new era. With an established food source and sustainable farming techniques in place, the prospect of solving modern food shortages became more tangible. The mission demonstrated that, with advanced technology and determination, even the mightiest creatures of the past could be tamed and utilized for humanity's survival. However, new threats loomed on the horizon: unforeseen genetic mutations, aggressive species resistance, and potential disruptions in the time-space continuum hinted at greater challenges ahead. The team knew that their journey into the prehistoric era was just beginning, and the true test of their ingenuity had yet to come. As they continued to explore and adapt to this ancient world, they remained committed to their mission of ensuring food security for future generations. The domestication of dinosaurs was not just a scientific endeavor, it was a testament to humanity's resilience and ability to overcome even the most daunting challenges. Future challenges and considerations. As the team continued their work in the prehistoric era, they faced a number of new challenges and considerations. One of the most pressing issues was the potential for genetic mutations. The team's DNA modification efforts had been successful in creating more docile and manageable dinosaurs, but there was always the risk of unintended consequences. Mutations could lead to new, unpredictable behaviors or physical traits that could pose a threat to the team's safety and the success of their mission. Another challenge was the resistance of certain species to domestication. While some dinosaurs had adapted well to captivity, others remained fiercely independent and aggressive. The team would need to continue developing new methods and techniques to overcome these challenges and ensure the success of their domestication efforts. Finally, there was the ever-present risk of disruptions in the time-space continuum. The team's presence in the prehistoric era had already had a significant impact on the environment and the behavior of the dinosaurs. Any further disruptions could have unforeseen consequences, potentially altering the course of history and jeopardizing the team's mission. Despite these challenges, the team remained committed to their goal of domesticating dinosaurs for sustainable food production. They knew that their work had the potential to revolutionize the way humanity approached food security, and that the lessons they learned in the prehistoric era could be applied to modern agricultural systems. As they continued to explore and adapt to this ancient world, they remained hopeful that their efforts would lead to a brighter, more sustainable future for all.